Alright, so here we are trying to find the critical load for a column with one end fixed. There's at this end here and the other end free, right? Okay. We're trying to find the equation for the critical load. Yeah, we're trying to find the critical load. So to do this, what we do is that we consider a section of the whole column, right? A section of the whole column. So we just look at it at let's see, look at it at this, just this section here, right? So we are just considering just this side, and when we get the equation and then put everything in to get what do you call it, the whole equation for the whole end, for the whole column, right? So this is how we do it. Because this compressive force P applied here, there'll be a deflection at A and a deflection at B, which is A, and deflection at X, which is Y, right? So now, as we said, we are trying to find the deflection at what's the name? At just X here, right? Which is Y. So this is what happens. We now have to find the moment there, which we know moment to be equal to force times distance, right? But this is what we do. From what we've done so far, we've seen that if we have a centroidal axis and we are trying to, let's say there's a curve here, right, something like this, and we are trying to get the distance from here to here, there's a way to do it. And if we have a centroidal axis here and we are trying to get the distance from, let's say, a curve which is of this sort, there's a way to do it, right? Okay. If we have the centroidal axis and we are trying to read the distance to this is a convex curve, we actually read the distance to be positive, right? Positive y. But if we have a centroidal axis and we're trying to read the distance to a concave curve or a concave deflection or whatever, the distance we say is negative. Are we okay? Okay. So it's with this that we are going to continue to get the equation. So let's move on. So now, because we are considering there's a section at X here, what we say is that the moment at that point, right, is equal to, we have the force already, P, right, and the distance. And because it's moving, we are getting the distance up to this convex curve here, right, which is the deflection. It becomes a positive distance. So we have something positive here, not negative, right, because of distance. And the distance that we are trying to get is actually A minus Y, right? So this is what we have. And then this M, or the moment, we know it to be EI Y second derivative, right? So it's with this that we'll continue to get whatever it is that we need. Let's move on. So now we can equate these two and say that EI YII is equal to P into bracket A minus Y, right? When we expand this, we get EI Y second derivative is equal to PA minus PY, isn't it? Okay. And then what we are trying to do is that we're trying to find the critical load. So the easiest way to do that is to make sure we have all our y's on one side and everything that without a y should go on the other side. So this is what we get. Let's see. We have E I, right, YII, right, plus PY equal to PA, right? And then the general solution for an equation of this form, general solution for an equation of this form is y is equal to, we have a constant, I'm choosing to make it a, and then we have a cos, right, into bracket p, a minute, bracket square root of p on EI, right, plus an L here, yes, plus B, let's make this smaller, okay, plus B sine, this is the general solution, it's bracket L times square root of P on EI right, plus a, right? This a because of this one right here, right? General solution. So now we move on. To make our work easier and clearer when we are going on, we will try to represent something complex. So this right here, we can see that k is equal to p on ei, right? K squared. This implies that k is equal to square root of p on ei, right? So with this we move on. Now the next thing we do is to use the boundary conditions to find our constant, which we have to be a and then b, right? Everything else is unknown constant, a and b. Everything else will be known, right? Yeah, so we move on, and then we look at the end conditions, the boundary conditions we have for this beam. So at x, or at e rather, we have x to be equal to 0, right? And then at that point we'll have there will be no deflection there because it's a fixed end. Deflection will be 0, and at that same point we'll have our slope to be equal to 0, right? So it's with this boundary condition that we move, right? So yeah, so we can put in the first one directly. So if you put in x equal to 0, y equal to 0 into this equation, let's name it. Okay. Into equation 1, this is what we get. We get 0 is equal to a, right, cos bracket L. We know that square root of p something to be equal to k, right, plus b right, this L here should rather be x, because what did we see when we started? What we said was that we are considering just a portion of the entire column, right? Which we said is this. Let's go over it. Which we said we are considering just this side. Then with that, we find the general equation of it, right? So here will be x. Let's put that here. This will be x. Okay, and then we have x here. All right. So this is x, which we've now placed in. This is actually k. But we have this L here to be our x. So now when I put that in, we get 0, right? And then what's next? We have sine 0 times k plus a, right? So with this, we end up getting 0 is equal to cos of 0. Let's see. Okay. So cos of 0, and that gives us 1. So meaning we have a here. Meaning we have a here, right? Plus sine of 0. Let's see. Sine of 0, and that gives us 0, right? That's plus 0 plus a, which means that we have our a being equal to capital A being equal to minus a, right? The next thing to find is to be our b. We've exhausted this boundary condition. We use boundary conditions only once, right? So the next boundary condition we'll be able to use is this. But the problem here is we should be able to find slope, right? So we find the derivative of that function there, right? So this has to be So we have y derivative equal to, so all that in there is our k, right? So we get k, find the, first of all, find the derivative of this cos gives us minus sign, right? So let's see. And then the derivative of the inside is k, right? So that's minus k a, right? And then we have what? Sine of k, right? K x, right? And then derivative of the sine gives us cos, which is plus cos, so that's plus b, and then we have cos small cos, right? And then we have into bracket, our k should come out. So this is plus kb, right? Then cos into bracket k, right? X, and then when we find the derivative of this e, that's 0, right? So that's what we have. And now the next thing is to put the boundary conditions in. We have our y derivative to be, or slope to be 0, right? Minus k e sine, we have our x here to be 0, right? So to sine 0 is 0, right? That gives us 0. So this here becomes minus 0 plus cos of 0, right? Because our k here, sorry, not k, our x, because we are using this boundary condition right here, this one, that's the one we are using. So our x here is 0, this x here is 0 as well. So cos of 0, and that gives us 1. So we end up getting what? K b here, right? So that's k capital B. This means that kb is equal to 0, but our k cannot be equal to 0. So this implies that the b constant is 0, right? So the equation that we get finally will be this. So let's see. Okay. Now what we have to do is just to put the constant a and b into the equation we found first, and then we continue with whatever we have to do. Okay, so we have it now. So let's see. Okay, and then we have this right here to be the k, so we just put it in. Okay, this is the k, this is x k, and this right here is x k, right? And now we know our constants, so let's put it in. We have y is equal to this a here, capital A we found to be minus a, so that's minus a cos to bracket k x. Our b we found to be 0, right? So if that's 0, meaning all this tends to 0, right? And then we have a plus a, that's a, right? With this means that this is the general equation for the deflection for the section that we've selected. With this, we move on and continue to put in the values for the, what's the name? The values for the x and the y, considering the whole beam, right? So now let's go back to it and look at what we have. Right? So before we go, we have y here. A doesn't change, A is not changing, K is not changing. X and Y are the only thing that can change. So now we derive this equation considering just this portion of the beam, just this side, right? So what we do now is will be to consider the entire beam, right? Putting in the values there. So at the very end, this very end here, we'll have our x being L, and we'll have our y being the E, right? The deflection at that point, right? So the A is y. So the y is E rather. So this is what we get. So let's write it out. So at B, right, y is equal to E, and then the the x rather is equal to L. So that's what we get. We get A is equal to minus E, right? Let's write this one. Minus E cos K L, right, plus E, right? What this means is that this takes care of this, so we end up getting 0 is equal to minus E cos K L, right? And because of the function cos, we can say this 0 here is equal to E cos of K L, right? But then clearly A cannot be equal to 0, right? So A is not 0. Let's see, so A is not equal to 0, so then we can clearly see that our cos of KL is equal to 0, right? But then again, now to get cos of KL being equal to 0, because of the way cos behaves, so let's see, cos of 90 gives us 0, right? So which is basically pi, right? If we move it to radians, that's what it would be. Yeah, so cos of 0, cos of cos of 90, which is pi on 2, right, gives us 0. So this is basically adding pi. When you add pi to this, like you're adding 180 is basically the same. So what's saying here is that KL could be, what do you call it, pi on 2 or plus pi, that gives us 3, so that's pi on 2, right? So that's half plus 1, a minute, 1 on 2 pi plus pi. You're basically adding 180, right? Plus pi it's given as a direct value. Well, yeah, so that's 3 on 2 pi. When we add another pi, basically adding pi. Those are the possible values that will make the cos function tend to 0, right? So that's 5 on 2 pi, right? So it could be anything or just adding, right? So now we are going to take the least possible value and then say that our KL is equal to 0, right? Sorry, our KL is equal to 2 pi. So if our KL is equal to, so this is the least practical. There's a whole understanding behind it, but we're not going to it. It's based on how the curve of the function will be. It has a particular wave, yeah. So let's see. So KL being equal to pi on 2. I'm going to write this. This is the least practical value, or the minimum value of, yeah, minimum value. Let's see, minimum value, least value. Least value. Right. Least value in the sense that we are trying to see the smallest. We are actually taking this one because we are actually trying, our aim is to find our critical load, and the critical load, we are trying to see the very least load at which the column will buckle. That's move from its initial position here, this purple one, from this purple position, from this purple position here to this red one. We are trying to see the least force. So if you are trying to see the least force, we consider the least, what do you call it? The least KL, right? So that's why we are doing it this way. And then we already said our KL, we had a value for it. We already said our K squared is equal to pi on EI, right? So this will imply that our K will be equal to square root of P on EI, right? So we move on and see square root of P on EI, right? L times L, all this, right, we go to pi on 2. And because our aim is the critical load P, right, we will have to bring that out, so we square both sides, this squared, this squared. So that gives us L squared times P, right, on EI being equal to pi squared on 4, and that gives us our P being equal to pi squared on 4, right? And then we have our EI here, right? And then the L squared comes here. Okay, so then our critical load is pi squared EI on 4L squared. And the L that we are having here is basically the length of it. And then this whole L, 4L, what do you call it, 4L squared are having, the 4L is actually the critical, sorry, the effective length, right? Yeah. So there's the equation that we have for the critical load for a column with the end conditions being one end fixed, which is at A, and then we have the other end fixed. Sorry, the other end free at B. So there's a column. Okay, so there's a column that we have, and we're trying to find the critical load, and then we went through all this to find this equation, which is the critical load equation for a column with one end fixed and the other end free. All right.